Hello everyone. I hope you're all safe and in good health. So I would like to welcome you to the video discussion on this course, Theory of Structures or Structural Analysis. This is your instructor, Engineer Edwin B. Rosalena. So this video includes the introduction to structural analysis and the distribution and the transmission of loads from one member to another. So let's start by defining a structure. So what is a structure? So a structure refers to a system of connected parts used to support a load, such as buildings, bridges, and towers. In other branches of engineering, this includes ships, aircraft frames, tanks, pressure vessel, mechanical systems, and electrical supporting structures. Then, what are the classifications of structures? So, number one, we have the tension structures. So, these are structures that are subjected to pure tension under the action of external loads. So, example, if we have the cables of the suspension bridge, so the cables here are in tension. So this is an example of a tension member. Another example is the knee brace of a building frame. So this is what we call a knee brace of a building frame. So when the frame is subjected to loads, so let us say we will have a lateral load for the building frame. So this knee brace is under tension. So this is an example of a tension member. Next, we have the compression structures. So these are structures that develop mainly compressive stresses under the action of external loads. So example is the opposite knee brace of the building frame here. So notice that when you have the lateral load here, this knee brace is in tension while the other is in compression. So this is also an example of a compression member. So meaning, not all knee braces are in tension. Some are also in compression. Then we have the columns of buildings. So when you have the load above it, then the columns are in compression. Another example of a compression structure are the arches. So arches are used for long span structures. So we have here example, an arch supporting a bridge. So when you have the loads on the bridge, then the arches here are in compression. The arches here are in compression. We have also the arch spanning the shell of a dome. So when you have the load on top of it, then the arches here are in compression. Next, we have the shear structures. So these are structures that develop mainly in plane shear with relatively small bending stresses under the action of external loads. So example of shear structures are the shear walls. So we have here the shear wall of the building. So when the building is acted by lateral loads, for example, the force of the wind, then the lateral forces are transmitted to the top of the shear wall, then transmitted down to the foundation. So the shear wall is in shear or shear structure. Next, we have the bending structures. So these are structures that develop mainly bending stresses under the action of external loads. So, for example, if we have the rigid frames, then we have the beams on it and the slabs, and we have the plates. No? So, we have here a rigid frame made up of reinforced concrete. So, this is made up of the columns and the beams, and then we have the slabs. No? So, if we have rigid frames, columns there are not only resisting compressive loads, but also they resist bending. So that is why some of the columns which resist also bending are called beam columns. So columns acted by compressive forces and at the same time resisting bending. Then we have the beams, which is a bending structure, and we have the slabs, which is also a bending structure. We have also here the building frame made up of structural steel. So we have the building frame, then we have this, the beams and the slabs. Okay? So, what is structural design and what are the criteria for design? So, as a structure is built, so it is built to serve a purpose for public. So, when designing a structure, the engineer must account for its safety, aesthetics, and serviceability, while taking into consideration also the economy and the environmental constraints. So, take note, we must have safety and serviceability of the structure. Then we have the aesthetics, and also we will design it considering the economy and the environmental constraints. So this requires several independent studies of different solutions before a final judgment can be made to which structural form is most appropriate. And this design process is both creative and technical, and requires a fundamental knowledge in the material properties and the laws of mechanics which govern material properties. So, dito na tayo papasok ngayon. So, the application of the laws of mechanics in the structural design. So, we must investigate or analyze the structure, and then we apply our laws of mechanics. So, that is why we have structural analysis before we can have the structural design. So, what is structural analysis? So, structural analysis is the prediction of the performance of a given structure under prescribed loads or other external effects, such as support movements and temperature changes. So, this is now our subject or the course, structural analysis or theory of structures. So, the performance characteristic that we are concerned on the design of structures are the following. So, number one, the stresses or stress resultant such as axial force, shear force, and bending moments. So, when the structure is being loaded, then the members there will be stressed. So, you know already what is stress in your lower course. We have the mechanics of deformable bodies. So, we have the stresses induced on the material due to the loads. So, stress is the internal effect of the member or the material when it is loaded. The next is the deflection or the deformation. When the structure is loaded, it will deform and the members there will deflect. So that is an external effect. So we will take into account also on it when we have the structural analysis and the design of the structure. And third, the support reactions. So, support reactions are the amount of the force which will be transmitted from one member to the other member supporting the member. So we will have the discussion on this later on the later part of this video. So that is how the loads from one member is being transmitted and distributed to the other members. So this means that structural analysis involves the determination of these quantities, stresses, deflection or deformations, and the support reactions that is caused by the given load condition. Okay, so alam na natin kung ano yung course natin, no? Theory of structures, and that is we will make structural analysis. So load on structures. Number one, we have the dead load. So the dead load consists of the weights of the various structural members and the weight of the objects that are permanently attached to the structure. So these are the weight of the material or the members of the structure and any object placed with constant magnitude and permanently attached to the structure. So for example, the dead load of a building structure include the weight of the frames, the bracing systems, the floors, the roofs, ceilings, walls, stairways, heating and air conditioning systems, plumbing, electrical systems, and so forth. So the table here are the unit weight of construction materials commonly used in construction of a structure. So we have aluminum. The unit weight is 25.9 in kilonewton per cubic meter. The brick, 18.8. Reinforced concrete, 23.6. Structural steel, 77. Then wood, we have 6.3. So that is about dead loads. Next, we have the live load. So the live load are loads of varying magnitudes and or positions caused by the use of the structure. So live loads are the use of the structure and the materials, or are the objects we placed on the structure with varying positions and varying magnitudes. So live loads for buildings are usually specified as uniformly distributed surface loads in pounds per square foot or in kilopascal. So the table below are the minimum floor live loads for some common types of buildings. So we have here the table, So occupancy or the use of the structure. Then we have the minimum floor live load. So these are minimum, minimum recommended. But in the evaluation of the structural engineer, if there is a need to increase the floor live load, then that's the discretion of the structural engineer. So assembly areas, we have fixed seats, 2.87 kilopascal. Movable seats, 4.79 kilopascal. Dance halls and ballrooms, 4.79. Garages, passenger cars only, 2.40 kilopascal. Then we have for the office buildings, storage warehouse, we have light storage, heavy storage, then residential, hotels and multi-family houses, then classrooms, schools. So just refer to the table. So if in case we design a structure, so we will be evaluating the live load that we will be using, the intensity of live load that we will use. So if in our evaluation the minimum floor live load will just okay for the computation or for the design, then we will just adapt the minimum floor live loads in this table. We have wind load. So wind load are produced by the flow of wind around the structure. So the magnitudes of wind that may act on a structure depend on the geographical location of the structure, obstructions in its surrounding terrain, and the geometry and vibration characteristics of the structure. So in the Philippines, our code, our NSCP, the National Structural Code of the Philippines, divided the map into 3 zones for wind load. So we have zone 1, zone 2, zone 3, with their corresponding wind velocity of 250, 200, and 150 kilometers per hour, respectively. Now, depending on the location of the location to which the structure is to be constructed. Then we have also the obstructions in the surroundings of the structure. So we have the exposure of the structure to wind. So it can be exposure B, exposure C, exposure D. You can read this in our NSCP about wind load. So exposure B, C, and D corresponding to obstructed area for B. Then we have for C little obstructions, and letter D we have the open terrain. Then we have also the geometry of the building and the enclosure of the building. So the building may be open, closed, or partially open. So we will take into consideration all those criteria when we compute for the wind load of the building. Number 4, we have snow loads. So in parts of the world where snow exists, roof loading due to snow can be quite severe, and therefore protection against possible failure is considered. So here in the Philippines, I think no snow loads is being considered. Earthquake loads. So earthquakes produce loadings on a structure through its interaction with the ground and its response characteristics. So this loading results from the structure's distortion caused by the ground motion and the lateral resistance of the structure. So we have a separate subject or course of this earthquake or the seismic analysis in our civil engineering curriculum. So next we have the hydrostatic and soil pressure. So when structures are used to retain water, soil, or granular materials, the pressure developed by these loadings becomes an important criterion for the design. So for example of such structures are the tanks, dams, ship, bulkheads, and the retaining walls. So when designing these structures, we will consider the pressures or the hydrostatic force acting on the structure. Okay, so we have here role of structural analysis in structural engineering projects. So structural engineering is the art of planning, designing, and constructing safe and economical structures that will serve their intended purposes. So take note, safe and economical structures. Okay? So we have here the phases of the structural designing. So the first is the planning phase. So the planning phase usually involves the establishment of the functional requirements of the proposed structure. the general layout, dimensions of the structure, consideration of the possible types of structures that we can adapt. It's either reinforced concrete or steel. Then we have also the consideration of non-structural factors such as aesthetics, environmental impact of the structure, and so on. So that is in the planning phase. Then we have the preliminary structural design. In the preliminary structural design phase, the sizes of the various members of the structural system selected in the planning phase are estimated based on approximate analysis. So, meaning, we have a trial sizes, and then we will do the preliminary analysis computation using the assumed sizes that we have. And that is in the preliminary structural design. So, estimation of loads. So, this involves the determination of all the loads that can be expected to act on the structure. So, all the loads that we have discussed in the previous slide. Then, we have here the structural analysis. So, in this phase, the values of the loads are used to carry out an analysis of the values of the loads are used to carry out an analysis of the structure in order to determine the stresses or the stress resultants in the members and the deflections at various points of the structure. Then we have the safety and serviceability checks. So, are the safety and serviceability requirements are satisfied based on our structural analysis? So, if yes, then we will go to the construction phase. But if the safety and serviceability checks are not satisfied, then we have to revise and do the redesign. Revise and redesign. So, go back to the preliminary estimation of load, structural analysis, and check for safety and serviceability. Okay? We have here plane structure versus space structure and the line diagram. So, in the figures here, figure 1A and figure 1B, this shows three-dimensional or space structure of a bridge in this case and of a building frame in this case. So, the analysis of three-dimensional or space structure is difficult. So, in our course, we will be dealing only with the two-dimensional or the plane structure. So, as you notice, these three-dimensional or space structures can be subdivided into two-dimensional or plane structures in which all the members and applied loads lie on the same plane. So, we will show it later in figure how we will subdivide this into two-dimensional or plane structures. Now, of course, the analysis of two-dimensional is easier compared to three-dimensional. That is why we adapt the two-dimensional or plane structures in our discussion because this is purely manual. Purely manual so that we can fully understand how we analyze a structure. But in the development of computers, the analysis of three-dimensional or space structure can be done easily. But in our case, we will have the two-dimensional or plane structure only. We have a little on space structures. That is only that is in their reactions and how the members will be stressed, or the loads, how the loads of the members in three-dimensional be computed, but we will not go deeper on that, no? So we will go deeper in the members of the two-dimensional or plane structures. So the analytical model of either two or three-dimensional body for analysis is represented by line diagram, in which in the line diagram, the members are represented by lines coinciding with their centroidal axis. The dimensions of the members and size of the connections are not shown in the diagram. Okay? So if we go back, this is for the bridge, no? So we have a three-dimensional bridge, then the trusses here can be drawn into a two-dimensional or plane structure. In this case also, the building frame that we have here can be broken into many frames, no? So we can have this front here frame, this side frame here, then we have the inner frames, no? So we can consider them one by one. So we have here the two-dimensional representation of the bridge truss. Then we have here the actual bolted connection. Then we can draw the line diagram. So the members are replaced by lines. Then we have here the bolted connection. This is replaced by the hinge connection in the line diagram. Okay. Then for the building frame, this is the two-dimensional frame of the front here. So I will draw it in two-dimensional structure we have here. Then we have the line diagram representing the frame. Okay, so that is why in our computation later, we will be dealing with two-dimensional, and then we have the line diagram. So we have now the load distribution of floor frames. So we will start with the floor frame of a building. A floor system is composed of slabs, beams, and girders, and the supporting columns of the girders. So slabs, beams, girders composing the floor system, and then we have also the columns supporting the girders. Okay. So a tributary area is the portion of the slab area carried by a particular member. So beam, girder, or column. Then during the design process, the engineer must calculate how much is the total distributed load carried by each member. So you have here the types of slabs. So reinforced concrete slab is a large flat plate in a structure that supports the live load and transmit it to the supporting beams. So the following are the types of the reinforced concrete slab that we will consider here in our discussion. One-way slab. A slab supported on two opposite edges only, or on four edges, but the ratio of the short span to long span is less than 0.5. It is called a one-way slab since the bending occur in one direction only, that is, in the short direction only. So we have here the figure of a one-way slab. So a slab supported by beams on two opposite edges only. So no supporting beam on the other two edges. So this is a one-way slab. So when you have the load, then this will deflect like this, or bend in one direction only. Or it may that the slab is supported by beams in each edge. So we have the four beams, one on each edge of the slab. But take note, the ratio of the short span to the long span should not exceed 0.5. short span and then long span. So when you have the loads, this is also a one-way slab and will bend along the short direction only. So that is why we call it a one-way slab. So one-way slab loads are distributed to the supporting beams as shown below. So even if we have beams here or girders, if this is a one-way slab, then the loads are distributed like this. One half of the short span, so this part here is carried by B1. This part here is carried by the beam B2. And the reactions for this beam, the reaction for these beams are to be carried on this girder or beam. Okay? So, pag one-way slab, that is only one half of the width of the tributary area. The one half of it is carried by beam on that part. Then the other is carried by the beam on the other part. And then we have two-way slab. So, a slab supported on all four edges, and the ratio of the short span to long span is greater than or equal to 0.5. So, it is called a two-way slab because bending occur in both the short and long directions. Okay? So, there are beam supports at all the four edges. Then, the ratio of the short span to the long span should be greater than or equal to 0.5. So, we call it a two-way slab because when we have the loads on it, this will bend in both directions. It will bend in the short direction. At the same time, it will bend in the long direction. So, the loads of the two-way slab are distributed as shown here. So, if this is a two-way slab, then we have here beam B1, B2, B3, B4. So, the loads are distributed like this, trapezoidal and triangular. So, this is at 45 degrees here. This is at 45 degree angle. So, tributary area for B1, tributary area for B2, triangular distribution for the tributary area of B3 and B4. Okay? So, we can now have sample problems for this. Okay, problem. The floor of a building shown in figure TH-332 is subjected to the following loads. So, superimposed dead load 2.8 kilopascals, superimposed live load 6 kilopascals. Then CD and EF are W310 by 86 kilogram per meter. When you say W310 by 86, W represents wide flange, no? So that is the steel section, no? Steel section, and 86 is the weight per meter. 86 or the mass per meter, no? 86 kilogram per meter. Then AB, GH, AG, and BH are W310 by 97. Concrete slab thickness 100 mm, unit weight of concrete 24 kilonewton per cubic meter. Then we have 3 questions, na? Siguro it's best if we will see the figure first. Okay. So we have the floor system made up of the girder AG, BF, BH, then AB, CD, EF, GH. Then we have here the columns. This is plan or top view, na? This is plan or top view. So these are the columns, steel columns, not reinforced concrete. So this is standing vertically. Then we have here the beams and then the girders. Okay? So CD and EF are W310 by 86. Ito, W310 by 86. AB, GH, AG, BH. Ito, AB, GH, AG, and BH are W310 by 97. Then we have the slab here, the slab here, that is 100 mm thick reinforced concrete slab. So question number 1, compute the total uniformly distributed service load on member CD. I think the questions are written here. So number 1, compute the total uniformly distributed service load in kilonewton per meter on beam CD. So itong beam na to, no? CD. Okay. So first, we will check what type of slab is supported by the beams. Tingnan natin, ha? Okay. So if we check the type of slab, so we have here, check the type of slab. This is 6 long span. This is 2.5 the short span. Ito 2.5. So the ratio of short span to long span is 2.5 over 6. That is 0.42. So the slab here is one-way slab. So if you consider CD, beam CD, the tributary area is 1/2 of 2.5 to be carried here. On the other side, 1/2 to be carried here. This part of the slab is carried on this beam. This part of the slab is carried on this beam. So if we have beam CD, this is the tributary area, and that is 2.5 by 6. So how will we compute for the loads? So una, we will have the uniform dead load, the superimposed, na? So the superimposed dead load as given here, this is 2.8 kilopascal. Kilopascal is kilonewton per square meter. And our question here is in kilonewton per meter. Uniform load. Okay. So to compute, our uniform dead load is equal to the intensity of dead load, that is 2.8 kilonewton per square meter, multiplied by the width of the tributary area, which is 2.5 meters. The width of the tributary area. So the result here, 2.8 times 2.5 is 7 kilonewton per meter. What's the meaning of the 7 kilonewton per meter? Meaning, for the beam CD, for every 1 meter length of beam CD, it carries 7 kilonewtons. For every meter length of beam CD, it carries a load of 7 kilonewton. So that's the meaning of the uniformly distributed load in kilonewton per meter. The intensity, kilonewton per square meter, meaning for every 1 square meter here of the slab, for every 1 square meter, this carries 2.8 kilonewtons. So see the difference? Kilonewton per square meter and kilonewton per meter. Okay? So kilonewton per square meter for every 1 square meter area. So the load is 2.8 kilonewtons. While if you consider beam CD and the load there is 7 kilonewton per meter uniformly distributed, so for every 1 meter length of the beam CD, it carries 7 kilonewtons. The same way for the superimposed live load. So the uniform live load is equal to the intensity of live load, which is 6 kilonewton per square meter, times the width of the tributary area, which is 2.5 meters. That is 15 kilonewton per meter length of beam CD. Okay, so we have already the dead load and the live load. We will compute the other force or load, weights to be considered. The beam is carrying the slab. So we will compute for the slab. And the beam also carries its own weight. So we will compute the weight of the member. Okay. So the weight of the slab is unit weight of concrete times the area of the cross-section. So can you imagine? The unit weight of concrete is 24 kilonewton per cubic meter. And then the cross-section of the slab carried by beam CD is 2.5 by 0.1. So saan to makikita tong 2.5 by 0.1? So that is the width here, the cross-section. If you have the elevation, the width here is 2.5 and the thickness is 0.1. So that is why we have 2.5 by 0.1 thickness. So the result, that is 6 kilonewton per meter. So meaning, for every 1 meter length of the beam CD, the slab weight it carries is equal to 6 kilonewton per meter length. Okay? Then we have the weight of the beam. So the weight of the beam is 86 kilogram per meter. Convert it into kilonewton per meter. So kilogram times 981 meter per second squared to convert to newtons. Then divide by 1,000 to convert to kilonewton per meter. Okay? So what is now the total uniform load of beam CD? So the total uniform load of beam CD is composed of the dead load plus the live load plus the weight of the slab plus the weight of the beam. So weight, dead load, and live load in the previous slide. So 7, 15, then we have 6, then 0.84. So this is equal to 28.84 kilonewton per meter. Okay? Next, we have here. So, later, we will view how the load is being distributed to the beam. Number 2, compute the total uniformly distributed service load in kilonewton per meter on beam AB. Okay. So, beam AB na. So, beam AB is here and this is a one-way slab. So, half of 2.5, that is 1.25, is carried by beam AB. So, uniform dead load, intensity times width of the tributary area, 2.8 times 1.25, 3.5 kilonewton per meter. Uniform live load, 6 times width of the tributary area, 7.5 kilonewton per meter. Weight of the slab, so 24 times the cross-section, 1.25 times 0.1. So you have 3 kilonewton per meter. Then we have the weight of the beam, so 97 kilogram per meter, convert to kilonewton per meter. I think this is very much similar to question number 1. So the total uniform load of beam CD or beam AB is weight dead load, uniform live load, or uniform distributed load of the slab, then the weight of the beam. So 3.5, 7.5, 3 plus 0.95 is 14.95. Okay? So the third question is, compute the total concentrated service load in kilonewton on column at A. Okay. So kung tingnan natin, column at A na, ibalik ko muna sa figure na. Okay. I think saan yung column sa A? Okay. So this is the column at A. So the column at A carries the reaction of AB, then carries also the reaction of the girder AG. And the girder AG carries the reaction at C of beam CD, reaction at E of beam EF. By the way, beam CD and beam EF are just the same. Can you follow? Then we have also the reaction of beam GH. Okay, so ito yung girder AG natin, tapos ito yung column A. So tingnan natin balik natin dito. Saan na yun? Okay. Ito, na. So, if you consider CD, the uniformly distributed load of CD is 28.84 as computed in number 1. Then, we have the reaction RC and RD. But because of symmetry, the reaction RC is just the same as the reaction RD. So, we can compute for RC or RD. They have the same value. So 2RC is equal to 28.84 times 6. Upward forces equal to downward forces. Or you can use summation of moments. So RC is 86.52. We can have also the load on beam AB. So the uniform load is 14.95. Then we have RA, RB. But RB and RA are just the same because of symmetry. So summation of vertical forces to RA equal to 1495 times 6. So we have 44.85. So if you consider now girder AG, ito yung girder AG natin. So this is due to the reaction at A of beam AB. Now, beam AB and the other beam here, I think this is GH, are just the same. Okay, kita? So we have the same reaction here. This is the reaction at C of beam CD and the reaction at E of beam EF. The same, na? Ito yan, 8652, 4485. 8652, 4485. And then we have the weight of girder AG. Now, girder AG is the same as beam AB. So we have 0.95 kilonewton per meter. So we have now the reactions AY and GH. Okay? So summation of forces. So we have here AY. Summation of forces to AY because GY and AY are just equal. So dalawang 48.85, dalawang 86.52, tapos the total weight of the girder. So 0.95 times 7.5. So AY is 134.93. And this is the concentrated or the compressive force carried by column A. So this is the answer of the question. That is the force carried by column AB. Or column A. Column A. Okay lang? So yan na. So that is from the slab, then we transmit the load from the slab to the beams, then we transmit the load of the beams to the girders, and from the girders to the columns. That is how we transmit the loads. Okay? So I think there is one more example here. Okay. The floor of a building shown in figure TH-333, itong figure na to, is subjected to the following loads. So A, B, C, D, E, F, G, H. A, B, C, D, E, F, G, H are W250 by 115. Then A, G, and B, H, W310 by 74. Concrete slab, 110 mm. Unit weight of concrete, 23.54 kilonewton per cubic meter. I think we have the same problem and tingnan natin ang questions, na? Same lang. Reaction at C and D of beam CD. Reaction of C and D of beam CD. Reaction at A and B on beam AB. Same lang, no? Then we have the total concentrated service load of column A. Okay. The same problem, but I think the difference here is the type of the slab that carried by the floor system, na? So we will check. So the short span here is 3.2, the long span is 5.4. Okay, so we will check, na? 3.2 over 5.4 is 0.59, greater than 0.5. So this is a two-way slab. So can you recall how the loads from the slab is distributed to the beams and girders for two-way slab? So this is the tributary area of CD. So 45 degrees here. Okay? So 3.2, half of it is 1.6. So this is also 1.6 here. Follow? Okay? So the same to compute for the value of the uniformly distributed load. For the uniform dead load, intensity, which is, take note, this is now 2.4 and 5.2, na? Okay. So 2.4 times width of the tributary area, 3.2, 7.68. Then, uniform live load, 5.2 times 3.2, 16.64. Weight of the slab, 2354 times cross-section. Width is 3.2, thickness is 110 mm or 0.11 meter na 8.29. Then the weight of the beam CD 115 kilogram per meter. The same na. The same computation procedure for the computation. So the total uniform load of beam CD is equal to this. You add all. But when you have the drawing of the load for beam CD, it is uniformly distributed up to this part here. But it varies to 0 up to the point C and D. So ito na yan. Ang load niya. So if you compute for RC and RD, so we have summation of forces. RC and RD are equal. So 2RC equal to 33.74. This is 2.2, no? Because we have 3.2 plus 2.2, so 5.4. Plus, we have twice of the triangular area. 1/2 33.74 times 1.6. So we have 66.11. So see the difference, na? If we have a two-way slab. Then we have here reaction at A and B on beam AB. So this is the tributary area. So compute the same, no? Intensity of dead load times width of tributary area 1.6. Live load the same. Weight of the slab same. The cross section is 1.6 by 0.11. Then weight of the beam. So the total load. But when you draw the load on the beam AD, ito yung makikita mo. 17.43 up to 2.2 lang. Then from here up to the ends A and B, it will vary to 0. Summation of forces vertical, we can come up with the reaction RA. Okay niya to, ha? You know this, how to solve, you know how to solve this, no? RA plus RA, so that is why we have 2RA equal to 17.43 times 2.2 plus twice of the area of the triangle. 1/2 17.43 times 1.6. 33.12. Okay? Then the third question is the total concentrated service load in kilonewton on column at A. So the column or the girder AG carries the reactions at A, C, E, and G. We have here 3312 here for AB and GH. Then we have 66.11 for CD. 66.11 for CD and EF. Then we still have the load, the triangular load, because if you notice, kung balikan natin to, we have the triangular load here. Here, so ito yung tributary area sa AB. So there is a triangular load carried by the girder. So we have here. Then we have also the weight of the girder itself. So this is also 16.3. So weight of girder, then the total triangular load for girder AB. So 16.3, 0.84, 832, 4.14. Dead load, live load, and slab lang. Dead load, live load, and slab. Okay? So we can now compute. Sum up forces vertical, and GY equal to AY equal to the total of these loads here. So tingnan nyo na lang yan, dalawang 3312, dalawang 6611, tapos the total load or the total weight of the girder. Ito yung area sa triangles, 1/2 16.3, then 3.2, then we have 3 of it, 1, 2, 3. Then 141.854. Okay, so that is all about the introduction and the distribution of loads. No? How the loads from one member to the other is transmitted. No? Then how will we compute it? So that is why we have the computation of the loads and the reactions. No? Okay, so thank you for viewing this video. No? Stay safe, everyone. Good health, and God bless us all. So, stay tuned for the next video.